First of all, I'd like to thank the Professor Xiaomin Tao, Feng Yan, and Jian Zhen for and other organizers for inviting me to this special event on wearable tech. Today, I'm going to talk about the electronic skin or stretchable devices for the next generation wearables. So this is the outline of my presentation. After a brief introduction, I will first talk about the stretchable electronics with an emphasis for the application of smart apparel. And then we're going to talk about the ultra-thin electronics, organic photonics, and finally briefly touch the nanomesh electronics. So I always begin my story with showing the robotics hand. You may not be familiar with the electronic skin, but that is truly stretchable animal-like skin sensors that can detect the temperature and pressure distribution simultaneously. So we realized the first generation of electronic skin by fully utilizing the material softness of organic thin film transistors in 2003. Since then, we are working on the organic electronics, which are solution processable and compatible with the manufacturing on the plastic foils. So this movie shows you the our production line to manufacture the active matrix for large area sensors by using or by combining the printing process, which include the inkjet and the screen printing and the gravure offset. So here you can see the robot arms transferring the thin plastic foil that is temporarily supported by the glass substrate, and then fabricate the organic thin film transistor with high spatial resolution. Because all the manufacturing environment is kept to be very clean, like the class 10, so we can improve the yield and quality of thin film transistors very precisely. And then this movie shows you how our device works. So it doesn't look like flexible devices, but once that's manufactured on glass substrate, this kind of jumping motion may cause the fatal device failure. But because that's manufactured on mechanically durable plastic foils, it can achieve the high spatial resolution and a high data readout simultaneously. And also we can monitor the pressure distribution and the temperature distribution simultaneously. Because of the mechanical flexibility, our e-skin can be wrapped around the cylindrical bar, and then we can monitor the grip pressure in this three-dimensional configuration. So immediately after we manufacture the first generation of flexible or bendable TFTs for robot application, we instantly recognize how important to introduce the mechanical stretchability into the integrated circuit. So without stretchability, we cannot apply the e-skin onto a movable part like a joint of arms, or it is impossible to apply the e-skin onto a three-dimensionally curved surface like robot body. And since then, we are working very hard to realize the stretchable integrated circuit. So in the first trial, we put the two-dimensional array of rigid island that is embedded in rubber substrate. the organic thin film transistor can be manufactured on rigid iron. And finally, source drain and other electrodes are connected by utilizing the elastic conductors. When we stretch the integrated circuit, all the strains are accommodated with changing the length of wires. So in that way, we can achieve the stretchability over 150% without causing any major change of device characteristic. So in that development of elastic conductors were newly developed, and that achieved the high conductivity and high stretchability simultaneously. The ink formulation was very straightforward. So we add the silver flake with typical dimension of 2 to 3 micron among the fluorinated copolymer, and then mixed together and print once on elastic substrate and annealed at 140 degrees Celsius. So when we look at the cross-section of annealed elastic conductors, we eventually discovered the silver nanoparticles with typical dimension of 5 to 8 nanometer is uniformly and densely dispersed among the rubber matrix. So this was the key to achieve the high stretchability and a high conductivity simultaneously. Indeed, the uniformly dispersed nanoparticle ensure the efficient percolation through the nanoparticles. So this was a trick. And we prepared the elastic conductors that was put on the rubber substrate, and that can be used as the stretchable wires. And here you can see the 8x8 pressure sensors are put on the fingertip of soft grippers used for the robot. And then that can be connected by using the stretchable wires. So here you can see the soft balls and hard balls. It looks similar, but when we apply the same force, the soft ball can be deformed largely, while the hard ball cannot be deformed. And then the contacted area was so small. So in that way, we can distinguish the contacted area, a monitoring of contacted area to differentiate the hardness of the ball. And our elastic conductor can be printed on rubber substrate, and that can be transferred onto the textile substrate. And the textile substrate is easy to form the glove or wears or any kinds of shape. And in that way, we succeeded in introducing the electronic functions on the surface of glove to make the glove smart. So this technique is creating the new field of smart apparel or a textile. And the left figure shows you the state-of-the-art electromyogram monitoring system that can be that is largely used in sports evaluation. But here you can see the gel electrodes are put on the skin surface, and that is connected by external cable. And here you can see the external module. So this is widely used, yet that is not so convenient for monitoring athlete motion because the cables are troublesome and that can be easily detached during harsh motion of athlete. But now all the electronic elements are embedded into the sportswear, including electrodes, cables, and the readout module. So in that way, commercial product can monitor the ECG, EMG, body temperature, and motion and creating the new application opportunities in the field of sports or monitoring of posture balance or to quantitative evaluation of rehabilitation. The next movie show you our motion capturing system. So here, the 7 accelerometers are embedded into the sports wear to monitor the athlete motion. So this kind of motion capturing system is usually arranged by the multiple camera setting, and then users requires to put the markers. But this system doesn't require the multiple camera setting, and just simply wear the smart clothes and instantly start monitoring the or user's motion. Because it doesn't require the multiple camera setting, we can monitor the user's motion anywhere, anytime, even outside the door during the running or even golf course. It is so easy, and just 1 second calibration is needed, yet the data, it achieves the real-time monitoring. So one of the important application is sports. So here, so she is the Miss Umehara, who is the Japan's national team member of Taekwondo. And during the Corona pandemic, the Miss Umehara found it difficult to meet her coach for practice, but we sent our motion capturing system, and that eventually, I'm sorry that some characters written in Japanese, but she repeats this motion, and then that's precisely monitored by our smart wear, and data was transmitted to her coach, and she gets the online coaching. So this was actually used during the Corona situation. And another application is rehabilitation. The person with spinal cord injury participated in a rehabilitation session at the home with wearing our prototype and communicated with his physical therapist remotely. So this kind of remote medicine or diagnostic are getting more and more important.
Stretchable electronics.
And next, I want to show you a new development.
With DNP's new wiring and mounting technologies, stretchable electronics can offer a pleasant wearable experience. Unlike conventional glove-type devices, stretchable electronics can be attached flawlessly onto the wearable component. Here are some features of stretchable electronics. They are highly stretchable and have low resistivity. The resistance is stable while extended. Our devices are robust after stretching 1 million times. Any electronic component can be mounted onto the stretchable electronics. This is a smart glove with an inertial measurement unit attached using our technology. Our device can capture finger motion accurately with superior fit. Let's realize the metaverse together.
So in that way, the glove is getting smart, and that can be utilized the motion of fingers So it is so easy just to wear the glove. So this is the benefit to utilize the smart apparel. And another latest progress was the 3D ECG monitoring clothes. As many of you may know, the conventional holder requires the attachment of gel electrode that's connected to the readout module by external cables. So to put the gel electrode on the appropriate position of the body, so patients have to go to the hospital. This is the major bottleneck of this kind of approach. But now we succeeded in fabricating the smart wear to monitor the 3D ECG. So this device is quite durable, and we proved the mechanical durability of over 100 times washing. And one of the great benefits to utilize the smart wear is body mapping. In other words, the electrode or monitoring position could be appropriately set from the beginning when we manufacture the clothes. And we sent our prototype to the patient house by regular mail. And the patient just wear these clothes. And because of the nature of clothes, the electrode can be attached onto the appropriate position without bothering the medical doctor. So in that way, we succeeded in getting the ECG simply by sending our device to the patient house by mail. So this is the latest progress of smart wear. And then we are going to talk about the next topics of conformal sensors. Today's first speaker was Professor John Rogers, who made the epidermal electronics. And Professor Rogers succeeded in reducing the thickness of silicon tip down to a few microns. And in that way, he achieved the amazing conformability of the device onto the three-dimensionally curved human body. And as we briefly mentioned, we are working on the organic electronics that's compatible with the solution process and suitable for the large area electronics. And we manufacture the organic thin film devices onto the plastic substrate with a thickness of 1 micron, which is floating in the air. And one of the benefits to utilize the ultrathin device was to transform the ultrathin film devices to be stretchable by using the wrinkling structure or accordion-like structure. After manufacturing of organic devices on 1 micron thick substrate, we prepare the pre-stretching rubber and laminate the devices together. And after relaxation of pre-stretching, the plastic foil starts shrinking, yet the rubber starts shrinking, yet the plastic foil doesn't shrink at all. So in that way, the buckling structure can be easily formed. So when we look at the cross-section by SEM, you may see the buckling structure can be nicely formed. And if we look at the bending area very carefully, the bending radius may change from 10, 18, 20, or 15 micron. But our device doesn't cause any mechanical failure, even though that was bent at the sharp bending radius of 5 to 10 micron. And so in this way, we can easily transform the ultra-thin film devices to be stretchable like this. So this is the original length and start shrinking and coming back to the original length. And we can make the other semiconductor devices to be stretchable. So another example of the world first stretchable OLED. So we repeated the same procedure. So we manufactured the OLED on ultra-thin film with a thickness of 1 micron and transferred onto the pre-stretching rubber to make the wrinkling structure. And also we start the integrating the multiple electronic functions onto single ultra-thin plastic foil. So one of the example is ultra-thin pulse oximeter, where red OLED, green OLED are integrated with organic photo detector. Because it is kept to be super thin, the sensor attachment on fingertip doesn't cause any discomfort of wearing. Or even though user may move the finger slightly, the measured point doesn't deviate from the optimized position. So in that way, the ultra-thin device attachment realize the fairly a good robustness against the motion artifact. But this was just the single point detection. And then we manufacture the two-dimensional array of photo detectors, and that achieve the high spatial resolution of 500 dpi, and also that achieve the high readout speed of 41 frames per second. So in this development, our flexible imaging system can utilize both organic semiconductor for photo detector and low temperature polysilicon for thin film transistor. In other words, so this is the combination of organic and inorganic semiconductors, making the hybrid system with utilize the good optical properties of organic semiconductor and high mobility of inorganic semiconductors. So we manufacture the low temperature polysilicon TFT that was originally developed for the display. And then we put the intermediate insulating layer and then complete the fabrication of organic photo detectors with keeping the whole process temperature to be low. And this is the device structure of flexible organic photo detectors. And we utilize the 70 nanometer thick ITO as a cathode and deposit the zinc oxide as electron transporting layer. And the active layer is mixture of PMD PP3T and PCBM. And finally, we put the moly oxide and silver anode. So this is the typical characteristics of organic photo detectors. And that covers the almost all the visible wavelength. And also that can detect the near infrared. And 850 nanometer is widely used for the pulse oximeter. And that's achieve the reasonable on-off ratio. And the detectivity was very good, and the response time was as fast as the 150 microsecond. So such kind of high performance OPD could be manufactured on the surface of LTPS thin film transistors. And then you may see the stability of OPD. So some people may concern about the air stability of organic devices, but that may be true for the organic light emitting diode. But organic photodetector or organic photovoltaic cell have nearly solved the reliability issues, and then that achieved the reasonable air stability in addition to the mechanical stability. And thanks to a high speed of low temperature polysilicon that achieved the mobility over 40 square centimeters per volt second. And here is the waveform of time response of waveform. And this is the simulation. And once the mobility exceeds the 40, so, and then that exhibits the sufficient response time. And our low temperature polysilicon can meet this requirement. And then we work with the Japan display to make the wearable type imaging module that can detect the near infrared of 850 nanometer. And that can be integrated with the NIR light emitting diode at the edge. And just to put the such a flexible devices onto our arm. And then we succeeded in detecting the position of veins without integrating with conventional optical lens. Now, our device can detect the fingertip that requires high spatial resolution. Simultaneously, we succeeded monitoring the pulse waves because of our fast readout speed. So in that way, our conformal imaging system can monitor the biometric information like the fingerprint or position of veins. Simultaneously, that can monitor like the pulse wave, like biological information. And finally, I'm going to quickly talk about the nanomesh device. It firmly adheres to the shape of the skin, and it is ultra thin, lightweight, and there is no sense of fit. So let me show you one video describing our latest progress. I'm Takao Someya, a professor at the University of Tokyo. Our on-skin sensor utilizing nanomesh electrode is ultra-thin, lightweight, stretchable, and breathable. It is capable of monitoring health conditions simply by pasting it onto the skin. New sensor can be worn on the skin continuously for a week without causing any inflammatory issues. Our skin display is a 24 by 16 array of micro LEDs, and it exhibits simple graphic with motion because it is made from thin and soft materials. It can be freely deformed. The skin display also showed an electrocardiogram measured by using nanomesh electrodes. Combined with a wireless communication module, the acquired biometric data can be transferred to a medical cloud, and your home doctor can monitor your health conditions while you stay at home. In the future, we envision human-friendly skin electronics that will lead to improving the quality of human life. Okay, so this slide shows you the fabrication of a nanomesh device. The polyvinyl alcohol is used to form the nanomesh by electrospinning method, and the gold patterns are formed by vacuum sublimation through a shadow mask. This device was put on the surface of the skin, and the water is applied by spraying, and the PVA is dissolved water and washed away completely. And finally, the porous gold film remains. In other words, PVA is used as sacrificed layer, and only thin film gold remains on the surface of skin. And the shining part is the gold. It looks like a thin film gold, continuous film, but obviously, when we look at the SEM, that exhibits the porous structure. And this is the magnified image. And if we look at the dark spots, that's the sweat pores. And we should look at the gold region or non-covered region carefully. The same amount of sweat are penetrating from the sweat pore because of the porous structure. Such kind of natural penetration of sweat or vaporization of sweat was critically important to ensure the biocompatibility. Indeed, when nanomesh are put on the people's forearm for a week continuously, the nanomesh doesn't cause any doubtful inflammatory issues. However, if the 1 micron thick polyethylene or 1 millimeter thick silicone are put on the forearm for a week as a reference sample, that exhibits the fairly large risk of inflammatory issues. So in that way, we proved the breathability is important to ensure the biocompatibility, particularly that is important for long-term continuous health monitoring. And then nanomesh is put near chest, and that is connected to the E-Veri band, connecting the electrode and wires and external module. And electrocardiogram waveforms were precisely monitored and transmitted to the smartphone in real time. So this slide shows you the pathway for the skin electronics. And we began with the development of robotic skin, and that required stretchability. And by thinning the entire system and going to make the whole system to be conformable. At that time, we expand the target object from the robot body to the human body, start monitoring the biological information. But long-term sensor attachment requires biocompatibility. And then we introduced the gas permeability to improve the biocompatibility. So before concluding my talk, I'd like to acknowledge my collaborator. So this is the group photo of my group who developed the Ultrathin stretchable devices. And the clinical evaluation were performed in collaboration with the Keio University Hospital, led by Professor Amagai. So in summary and conclusion, today I talk about the recent progress of on-skin device or smart apparel. And by utilizing the material softness, we try to improve the harmonization with human body. And such a novel electronics is expected to open up the new application opportunities in the field of healthcare, medical welfare, sports, and even more. So thank you very much for your kind attention.
Professor Someya, thank you very much for exciting talk. And I see your work on apparel are quite impressive, actually. Now, you're talking about the future. What is your opinion on the skin-mounted device compared with apparel wearable devices? What are the good things? What are the challenges? Can you enlighten us on these points?
Okay, so thank you very much for asking the quite important question. The people, of course, hate the direct attachment of something onto the human body, but with establishing the good physical contact on skin, we expect the accuracy of biosignal monitoring. However, we have to improve the biocompatibility, particularly that is necessary to achieve the long-term health monitoring. And we have to improve the mechanical durability of soft breathable sensors. And it is not too difficult to improve the durability of nanomesh device. But when we improve the mechanical durability of nanomesh, and going to be a little bit hard material, and then human skin is so sensitive, and then that starts detecting something or attached, and cause the irritation or itchiness. So that is quite tricky situation. So we have to meet all the requirements. So mechanical durability and the biocompatibility, and that is the key to achieve the long-term health monitoring, that I believe.
Oh, hi, Professor Someyya. Thank you very much for giving the excellent talk. So I'm Feng Yan. Thank you for accepting our invitation. So I have a few questions about, for example, you have this micro imaging device to be attached on the surface of the finger, right? And you can find the fingerprint. You can find the image of the veins, right? But you just have this array of photo detectors. How can you change the focus? It's at different depths.
Okay, so that is important question. So we made the we didn't utilize the conventional lens. So that means the spatial resolution is getting worse when we try to detect the depth profile. So we didn't use any conventional lens, but we laminate the sort of how can I say, we say privacy sheet used for the smartphone. So and then try to slightly improve the spatial resolution. But as you mentioned, the spatial resolution of the body in depth is not so great. So that is one of the important future homework. But because we try to get the high spatial resolution near skin, so currently our device can achieve the sufficient spatial resolution, even without the integration of a conventional lens.
Okay, that's great. Do you use some light source to illuminate the finger?
Yes. So light. So we have two different types of light illumination. One is the just when we put the here is the detector, and then put the light source in transparent geometry. But also we integrated the light source and photo detector on the same device, and then put the finger tip and detect the fingertip. So in other words, the light is propagating from the edge by using the scattering. So there are a couple of ways to achieve the fairly uniform irradiation of incident light.